Okay, so welcome to lecture 2 of module 11 in testing. So, built-in self-test. So, in the last lecture we were looking at this case that with the assumption that whatever test patterns or whatever testing we were discussing at length were for offline testing. So, what do you mean by offline testing? That is the circuit had been fabricated and it is put in the ATE and we are applying test patterns to test it. But then we also saw that nowadays due to the deep submicron design, what happens that even if the circuit is fine when you have sold it off or when it has been shipped to the vendor, shipped from the vendor to the customer, even after putting into the system it may have failures because of the deep submicron designs. So, all these type of soft failures and what you can call in situ failures are increasing in picture. So, to have them, what the idea was that to test that. So, what we did is that if we found out that we can develop a technique in which case what we can do, we can put a miniature version of the test pattern generator and a miniature version or what you can call a subset version of the test pattern analyzer or test pattern comparator on chip. So, now every time when your chip starts your operation, what you do, you activate your test pattern generator and that is the miniature version which is kept on chip, and you use your random test and your test comparator to find out if anything is gone wrong. So, if you can do that at every startup of your circuit, actually we call it as a built-in self-test. So, in the last lecture we have seen that what we basically require in BIST architecture. So, we require a test controller, we require a test pattern generator and its size should be or area should be very less because it is an on chip circuit. So, that area constraint is very high. So, we have seen that we can use linear feedback shift registers and we have seen a standard LFSR and how using a series of simple XOR 2 input XOR gates we can easily develop a near exhaustive kind of test pattern. They are just like excluding the case of all zeros, we can generate patterns from 1 to the power n minus 1 kind of a stuff, and a subset of them are required for testing, and the area requirement is nothing but a single XOR gate as we have seen in an example in the end of last lecture, or it can be XMAT a few XOR gates. So, and that is much less than the gate required by a deterministic test pattern generator that will like you count like 1, 3, 5, 7, 9, 11, 32 something like that. So, if you go for deterministic test pattern generator like this, so on chip circuit will be very high because you have to go for finite state machine design or gate optimization and all, and finally you can see that you will require much more than a few XOR gate, which is the case in the case of standard feedback LFSRs or standard LFSR or any other type we will see. The basic idea is that the pseudo random test pattern generation using linear feedback shift registers are much more area much more less in area compared to standard deterministic test pattern generator by using the finite state machine approach of digital electronics if you do. So, because of this low area requirement of LFSRs, we find them a very good candidate for BIST pattern generator in case of built-in self-test. So, in the last lecture if you remember, so we have seen something kind of LFSR of this nature which we call the standard LFSR. Today we will see another type of LFSR, but why do we require another type of LFSR? Let us just quickly get the motivation. So, what was the idea is that you can see that in case of a standard LFSR, there is a chain of XOR gates, like if there is also another feedback from this XOR gate. So, you require another XOR gate over here, this input will be there and this will be feeding this and so forth. So, the delay may increase in case of LFSRs because if you have a very high number of XOR gates, as you can see, if all these H's are 1, then 1, 2, 3, 4 dot n H's or n minus 1 XOR 2 input XOR gates will be there which will be feeding this one. So, there will be a lot of delay involved. So, to avoid this delay, so we will study a new type of LFSR today, that is actually called modular LFSR, and then also we will see for the response compactor and all those things. So, to avoid those delays, people have developed another kind of LFSR which is called the modular LFSR. Its job is almost the same, it will also have a characteristic polynomial, it will also generate near exhaustive random patterns. And same thing, the only advantage you will have here is that there will be delay will be less because in this case the architecture as you can see is a bit other way around. So, in this case there is no sequence of XOR gates. So, as in the case long chain of XOR gates are not there, so the delay will be minimized. So, what is the idea here? So, you put the XOR gates just like that, the D flip flop already as in case of standard LFSR, but now instead of having a chain of if you remember the standard LFSR, we had direct connection between these two, and this feedback to this back here actually you involved a lot of XOR gates. So, that actually caused the delay, but here we are not doing it, here the architecture is a bit different. Here there is a direct feedback from here to here, and each of the inputs of the XOR gate for the D registers you can either use a feedback from this or you may not use a feedback. Like in this case if h minus 1 is equal to 0, then there will be a direct connection, this feedback will not be used, and if this h2 is 1 say, then this feedback will be used by XOR gate from this one, and then only it will be given as the input the next flop. So, this is how is the basic architecture modular LFSR. So, in this case it is seen the difference in modular LFSR compared to standard LFSR is due to the position of the XOR gates. So, here the XOR gates are positioned in such a way, so that there is only one XOR gate which is in the delay between this one and this one. But in the previous case there was a lot of XOR gates was here. So, there is a lot of delay compared to the output of the last flip flop to the compared to the input of the first flip flop kind of a stuff. So, to avoid this we have now gone to this new architecture. In this case we have actually only one what you can call this one XOR gate which is actually which is the input of all the flip flops. So, the delays are in less. So, there is only one LFSR. In modular LFSR between adjacent pair of flip flops there is only one XOR gate. So, these LFSRs work faster than standard LFSR because at most one XOR gate is between the adjacent flip flop, while in case of the other one there can be a lot of gates in the feedback of standard LFSR. So, that is why we are moving to what you call modular LFSRs. Now, we will see just like in the previous case we will have matrix definition for this, then we will also have what you can call this characteristic polynomial and all. So, let us see. So, what is the case? So, in this case also if you want a feedback then, so here one thing is there. So, you have to remember that x naught input of x naught is equal to output of x naught plus 1. That means, if you say that x naught t plus 1 is nothing but equal to x naught x n minus 1 t. So, that has to be understood that whatever is the value here at the time t will be the value at this one at value here, that means here will be value t 1 plus 1. So, that is what first you have to establish. So, in this case also you can see here that if you consider this one is your diagonal matrix. So, this is your x naught to x n t plus 1, this is x naught. Okay. So, first one we already know that what is the value of x naught t plus 1, that is x naught t plus 1 will be nothing but x n minus 1 t naught, 1 will be the direct connection because there is a direct connection from here to here. Okay. So, that is what is the case. So, x naught t plus 1, this one is equal to all these will be multiplied by 0 0 0 0, only this one will be there because this one will be product with this one. So, you are going to get as x naught t plus 1 is equal to nothing but x naught x n minus 1 t. So, that is why this last column will have a 1 here. Okay. Now next we can see is how can you develop the expression for x1 t plus 1. So, if you see x1 t plus 1, this one is what? The x1 t plus 1 will depend on what? It will depend on this one. Okay. So, it will be obviously depending on this one. So, it will be what? It will be x naught t. Okay. XOR, there can be an XOR if H1 is 0, then this is directly dependent on there is a direct connection, then it will be nothing but x1 t plus 1 is equal to x naught t. But in this case H1 equal to 1, then this feedback will also come into picture, then you have to put XOR, what is that? X n minus 1 into t naught. So, into t, the previous t. Okay. So, this is not t naught, this is t. So, then the feedback will also come into picture. So, that is the thing you will get. So, x1 t plus 1 is what? It is nothing but this guy will be there. So, it will be this one product will be 1. So, it will be nothing but x naught t XOR. Okay. So, because of this one will be gone, sorry, this one will be gone, because of this will be product into 0, everything will go off because of all these zeros, excepting this H1 will be there, it will be H1 dot x n minus 1, this guy into t. So, this one. Okay. So, what it says that, so x n minus 1, this feedback will be considered if H1 is equal to 1, else it will be a direct feedback from this one. So, if H1 is equal to 0, if you consider, then this one will also be gone, this one will be gone. So, x naught t plus 1 will be nothing but only this first product x naught t plus x1 t plus 1 will be nothing but x naught t, only this one will be x naught t will be there. Okay. So, this is how you can develop for everything. So, just like let us also look at another flip flop, say in between. So, in between you can consider this is x naught n minus 3, you can consider this flip flop over here. So, it will depend on x naught x n minus 4 and also the feedback. So, just you can look at it. So, if you can consider x naught, say x naught, this one we consider, sorry, this one we can consider. So, it will depend on x n minus 3 as well as the feedback if required. Okay. So, it will be dependent on, so so this is your this thing. So, for this we will have a 1 over here. So, it will be depending on x n minus 3 will be there. So, this will be for, if you consider this row 0 0 1 1 0 H2 will be there because a diagonal element. So, it will be, you will have something x n minus 3 of t will be there. So, x n minus 2 of t plus 1 will be nothing but equal to this will be there, and this will be product with this guy because all others will be 0. So, it will be equal to x n minus 3 of t then you have to use an XOR, then it will this one will go off because of this product with this 0 it will go off, then h n minus 2 will be there in x naught h n minus 2 product of this one. Okay. So, this will be x n minus 1 of t. So, depending on whether this one is 1 or 0, so this factor, that means this 2 factor, that is h n minus 2 product of x n minus 1 t will be there or will not be there, will depend on this value. Otherwise, if this is there, then you will have to XOR this one with this factor, and if h n minus 2 is 0, then this will not be there, then x n minus 2 t plus 1 will be x n minus 3 into XOR into t. So, that is what is being obtained, that is each of this flip flop is dependent on the other flip flop XORed with the feedback of x n minus 1 if the corresponding h is 1, else it is a 0. So, that is a very simple this thing, very simple stuff. So, this can be easily represented by a matrix format as you have already seen. So, this is the matrix format. Here is you have a diagonal matrix over here like this row is all 0, here it is 1 and here it is the corresponding h's. So, similar to this, if you look at this our standard LFSR, if you look, so it is also having a similar stuff, but here everything is bit rotated. So, this is your standard diagonal matrix, okay, and this one is your this is this is all 0, sorry, just a minute. So, here this it is for the standard LFSR, already we discussed in the last class. So, this is your diagonal matrix. So, this is the column with all 0 and the 1 bit will be 1 and these are all the h's. So, this is just, and if you consider for the modular LFSR, this is nothing but it is a bit roundabout way, something has been rotated kind of a thing. But just by doing this, but they are actually equivalent in nature, but by using this type of rotated kind of an architecture, then the delay between this flop to this flop, this flop to this flop becomes very low, because we have only one XOR gate in between. So, that is why we have moved to something called modular LFSR, because of the delay constraints which we are avoiding in case of modular LFSRs compared to standard LFSR. So, whatever I told you is written here in text. So, in modular LFSR, the output of any flip flop may or may not participate in the XOR function. So, if the output of any flip flop is xi say provide input to the XOR gate with the feedback this one, then the corresponding h is 1, else it is a 0. So, that is whatever we have discussed, that the output of one flip flop will control the output of the output of one flip flop will control the output of another flip flop, but if you also want to depend on the feedback of the x n minus 1 flip flop, then the corresponding h should be 1. So, that is what actually is written over here. So, so again this equation will be x, this is the equation. So, x t s is this matrix is t of s, and it is the next value of a flip flop, and this is the present value of a flip flop. Okay. So, in this is what is the case. So, already we have discussed about how do you get these equations, and then again this is your characteristic polynomial. So, f x will have 1 here and x n. Okay, this is depending on the last two terms, and in between you will have these values depending on the values of h 1, if h1, h2, h3 dot hn minus 1 if you consider them to be 0 or consider them to be 1. So, based on that you can get the characteristic polynomial as same as in the case of a standard LFSR. So, only difference is that, so again lot of theories exist as we have discussed, as we were discussing in the last class, a lot of theories exist to find out whether this characteristic polynomial will generate a near complete set of random patterns, or whether it, and actually whether it will not, and also the case whether it may not be able to generate all those things. So, there are a lot of theories that exist, that given a characteristic polynomial like this, there can be a lot of analysis which can predict or which can say that or which can determine that if any modular LFSR has this polynomial, characteristic polynomial, then it will generate a near exhaustive random set of patterns excluding the all zeros, and sometimes there also exists some characteristic polynomial which will not generate the all possible exhaustive set of patterns. So, depending on your requirement you can select a characteristic polynomial, and how is the characteristic polynomial selected? Based on this, whether you require a feedback from this XOR gate or whether you require a like this. So, it is always a possibility. So, in this example the person has decided not to use this. So, he has required that only for the x3 flop you require a feedback from this, and for the other case does not require. So, here the characteristic polynomial will be, so 1, 2, 3, 4. So, polynomial will be 1 by x4 plus only his x3 is 0. So, it will be h3 x cube plus this one. So, this is 1. So, you can eliminate this. So, it will be 1 plus x cube plus x 4. So, this x3 and x 4 are already there, and x 3 is equal to the factor x 3 comes here because of h 3 is 1, and there is no product like h x 1 x square, because in this case these guys are 0, these h's are 0. So, they are removed from this characteristic polynomial. Now, there exists a literature. So, you can find out whether this characteristic polynomial generate a near exhaustive set of patterns. So, in this case if you look at it, you will find out that this characteristic polynomial fall in the class where you can generate the near exhaustive set of patterns. Now, what we have found out that there is another thing which also depends, as in the case of standard LFSR, there is one more thing that is important, is actually called the seed vector. Seed means what is the initial reset values. So, depending on that, this next series of, I mean you can also have series like this also, there is no one can prevent you from that. So, you can also have this as the seed vector, then you will start from this one, and you can have any other seed vector, then you can start from that part, that vector. And it is very important to find out that how do you select the seed vectors. Then actually, for example, if you say that these are the 4 vectors which are actually used for my testability case. So, better I start from this one, then very quickly I will, from here up to here I will get all the required vectors for testing, and then my job will be done. Then I can reset back here. Then obviously I will give this as the seed vector. But if your very important, if your important test patterns are this one and this one, then obviously you will start from this seed vector and you will go forward from here, and you will not start from here. So, what is the idea? The seed vector will tell you where to start from, and then what is the sequence of patterns. So, obviously we will try to give such a seed vectors so that you can get the required test patterns for testing, which you want to keep for testing in the early sequence, right. So, that was the idea. Okay, so, what we are saying that, so that is already the same case existed in case of this standard LFSR, that we have to set the seed vectors, that is seed vector in such a way, so that very quickly we can get the required test patterns. So, in this case let us assume that the person has assumed that maybe this or this may be his important test vector. So, he has given this as the seed vector. Now, let us see how it happens, how we get these patterns. So, same example as in the previous case also. So, he has used x naught as 1 and others as 0. So, this one is his seed vector, sorry, this one is a seed vector, this one is a seed vector. Now, what next? So, this one, how do you write about it? So, we already know that this is our diagonal vector. So, diagonal matrix, so it is there, and then this one is all 0. So, first one you have to keep it as a 1, that is already there, and in this case it is h3 is 0, 1, h2 and h1 are 0. So, you get 0 0, and here you put a 1 because h3 is 1. So, this is how you develop the matrix, correct. So, now as we know that here x naught will determine x1, x1 will determine x2, x3 will determine x2 will determine x3, right, x naught will determine x1, x1 will determine x2, x2 will determine x3, and x3, sorry, there is a, so in this case x1 will determine x0 will determine x1, if here it is a direct control because there is no feedback is required, but if the feedback had been taken into picture, so x naught will control x1 with the feedback. So, in this case there is no feedback for this line. So, we can directly say that x naught is controlling x1, similarly there is no feedback over here. So, we can say that x1 is controlling x2, and in this case there is a feedback. So, x2 is controlling x3 with a feedback, and then directly again you can say that this x3 will be directly controlling x1. In this case there is no feedback. So, I mean no feedback involved. So, this is the direct control, and here actually from here to here, from here to here, and from here to here this is a control, but the control may involve an XOR from this one, but in this case there is no feedback, so it is a direct control, and in this case there is a feedback. So, there is a dependent control from x2 to x3. So, now if you can see what happens. So, in this case it is very easy. So, let this be the seed vector. So, it is 1, there is a 0, 0 and 1, 0, sorry 1, then 0, then 0 and then 0. This is the case. So, after the next iteration what will be the case? We know that. So, this was our control, here is an XOR control, and there is this control is there. So, obviously, so this value will come here, this value will come here, the third value will come here obviously with an this one. So, this value is coming here, this value is coming here, and this value will come here obviously with an XOR condition. So, in this case what happens? So, to determine the value of x3 we have to XOR 0 with this XOR. So, 0 XOR 0 is already a 0. So, we get a 0 over here, and you should also know that x3 will directly control x0. So, this value will go over here. So, very easily we can get the vector of 0 1 0 0. So, this is the case. These two are direct controls here, in this case no dependency, and in this case there is a this x2 is controlling x3, but with a XOR with this one. So, in this case is 0 XOR 0, so we get a 0 and this is the case, and this one will be directly feedback over here. So, we get 0 1 0 0 0. So, what is the next vector here? So, the next vector here will be nothing but it is 0 over here, then it is a 1 over here, it is a 0 over here, and it is again a 0 over here. So, this is how you get it. Okay, so, now you can again find out the next vector how you can determine. So, in this case we know that this one is a direct control, this one is a direct control. So, you get these values directly, but this third value will depend on the XOR value of this one and this one. So, again 0 XOR 0 is 0. So, you get this value over here, and this is the feedback from here to here. So, you get the vector 0 0 1 0. So, it is a 0 0, and now it is a 1 over here and it is a 0 over here. So, now you can see the fourth vector. So, fourth vector as we know, again these two are direct controls over here. Now, this control from here to here will depend on XOR of this value with XOR of this value. 0 XOR 1 is a 1. So, you get a 1 over here, and this one is actually having a feedback over here. So, now you get the value of 0 0 0, and so this one will be a 0 now, and this one will be a 1 now. So, this is what is your next vector over here. Similarly, it is very same way you can calculate this one, and this one will go here. So, the same way you can find out this whole sequence of patterns. So, you will find out that we started from 1 0 0 0. So, after so many patterns you will find out that there will be a repetition. So, if you count 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 patterns. So, 2 to the power n minus 1. If you are excluding the all 4 0. So, it is a exhaustive test pattern has been generated by using this characteristic polynomial. This was this heat. So, in this case if you have an application where you have to generate 4-bit vectors for your testing, and if you assume that these 3 are your these 3, you can say these 3 are your more important test patterns, and then this one. So, what you can do is that you can take this as a seed value, and then you will get patterns up to this, and then you can reset and you get your value done. And again, if you assume that these are your important test patterns, then you can have this as the seed value, and then you can go about this way. So, see, it is a very similar case. So, as a very similar case like modular LFSR or standard LFSR, whatever you take, the basic idea is that you can generate a near exhaustive set of random patterns, and the area over it is very less. So, in this case, as you can also see, there is only one XOR gate is involved, but in case of standard LFSR, from the feedback from the last feedback to the first flip-flop, the last flip-flop kind of a stuff, there is a feedback. So, the whole feedback mechanism from the first feedback to the last feedback, or somebody can say the last feedback to last flip-flop to the first flip-flop. So, whatever, the longest feedback in standard LFSR involved a sequence of XOR gates. So, that was leading to some kind of a delay. So, we went for modular LFSR. In modular LFSR, it is also the same case. We can have a characteristic polynomial, and we can select the characteristics polynomial in a very nice way by using a simple sequence of XOR gates, and you can similarly generate a near exhaustive set of test patterns. But here the delay will be very less, because in between one flip-flop, in between a pair of flip-flops, there can be at max only one XOR gate. So, modular LFSR has all the features that a standard LFSR has, but only with the added advantage that there is no extra delay or not extra huge delay because of the chain of XOR gates. So, again I was discussing many times whether any LFSR will generate all the 2 to the power n patterns. Actually, the answer is no. There is only a few characteristic polynomial for which is the maximum length. They are actually called primitive polynomial. So, they are a list. There people have found out a list, like this person in this paper. He has found out a list of such polynomials, so that you can have a reference look at that, and then if you want to design a circuit which requires an exhaustive set of patterns, then you can go about selecting a characteristics polynomial, that is called the primitive polynomial, and you will be able to generate what you can call a near exhaustive set of patterns. But sometimes you may not be requiring a huge set of 2 to the power n minus 1 patterns, even a very limited set of patterns will be enough. So, in that case you can go for selecting another different kind of characteristic polynomial which may not be a primitive polynomial. So, you need not generate the exhaustive set of patterns, you can generate a very particular set of patterns and a particular sequence. So, depending on the characteristic polynomial and whatever you can call the seed vector, you can get your desired random test pattern generator accordingly at a very low area cost. So, that is actually the beauty of what you call this linear feedback shift registers in case of BIST. So, major requirement in just to recall once more. So, major requirement in case of BIST is what we require pattern generator, but again the pattern generator cannot be a very huge area overhead pattern generator, because in case of ATE the area overhead of the pattern generator in case of an automatic test equipment is not at all of concern, because a huge equipment and you can do that. But whenever you are going for in situ testing, so all the chips will have on chip area test pattern generator. So this area is very restricted. So how you can do it? So one option is that you can generate a deterministic test pattern generator as we have done using a finite state machine based implementation as in our digital design fundamentals. But here the area overhead will be very high, because you have to optimize your number of gates, because in the standard procedure you know you have to generate a finite state machine with all the states and the sequence, and then you have to find out optimize the number of gates for each input of the flip flops, and this is the standard procedure we follow. But you can generally find that the number of gates will be much larger than a single XOR gate or a sequence of single 2 input XOR gates. Actually, the number of gates will be much larger if you are using a deterministic finite state machine to generate that. But then linear feedback shift registers like the modular LFSR or standard LFSR, they are actually very much great boon in this case, because by using a single sequence of 2 input XOR gates or a few number of XOR gates, you can generate the desired characteristic polynomial and a seed that will give you the sequence of patterns you require for doing the testing, and the area overhead is extremely smaller compared to a what you call a deterministic finite state machine based pattern generator. So that is why we all go for the LFSRs with the desired, we can design the LFSR with the desired primitive polynomial, desired what you call the characteristic polynomial, and if you do an exhaustive set, though you have to go for a primitive polynomial set, list can be found in this paper. And if you do not require that, you can design another kind of a characteristic polynomial, so that you may not have the exhaustive set of patterns, but you will have the required set of patterns. Again, if you want to select the sequence of patterns in such a way, so that your required test patterns arrive before, so you can select the seed accordingly and your job is done. So that is how we all design what you call the pattern generator in case of BIST using LFSRs. Okay, now the second part of your BIST design, as I told you, BIST has 3 components, main components basically, that is test controller that controls this one. So these are standard digital electronics fundamentals. How can you control your circuit? That is the control path design. Next was your standard test pattern generator, so which you have already solved using the LFSRs, that is the modular LFSR and standard LFSR. Now the remaining is another part is actually called the response compactor or response comparator. That is, the circuit will generate some responses based on your input patterns. So these input patterns already you know that given this LFSR, what is the pattern that will be generated by the circuit, and then also you can easily compute that what will be the normal response of the circuit corresponding to this pattern, say, because given a characteristic polynomial and then design, because this design is pre-made, so they are already fabricated in the circuit. So we know that this is the seed, so we know that this is the seed and this is the sequence of patterns that will be generated, and also we know that the circuit is, if the circuit is operating normally, then what will be the output response corresponding to this pattern, that is can be already calculated, and that can be stored in a ROM and it can be compared. But now you see, because the ROM is also a very expensive component when you are thinking on an on-chip design, then you cannot go for a flat design like you select the patterns from the test pattern generator, that is the LFSR, then for all these patterns you explicitly store the full output response of the circuit in a ROM, and then you can go for a comparison. These are called a flat design. This is the pattern, this is the output is stored in a ROM. You apply the inputs to the circuit and compare the responses using a comparator. This is a flat design. But now the ROM is very expensive, so here also what you have to do, you have to go for some amount of compaction or compression, so that your ROM area is very small and you save on something. But obviously when you are compressing, so these are lossy compression, so you can find out that there will be some loss in fault coverage. But still the major requirement what our case was here, in this case was that you have to go for a low area ROM design. So that can be achieved by compression. So that is what we will be now studying in this lecture. So that is what I told you, the expected golden response. Yeah. So that I already told you, the expected output response of the cannot be stored explicitly because of the size in the ROM. So in other words, what he is saying, in BIST it is necessary to compress the large number of cards, large number of card responses and the circuit under test responses to a manageable size, so that it can be stored in the memory and comparison. Okay, and also your target should be that there should not be any aliasing. So what do you mean by aliasing kind of a thing? So that that is the that if you do not compress, so a fault can be detected, and if you compress it, the fault may not be detected. So we will explain with an example. So if it happens that due to compression a fault is not been able to be detected, then it is called an aliasing. So your target should be you do such a compression so that aliasing is minimized. So that we will be explaining through example. So this is actually called, that will be more clearly. So some simple techniques of compression, there are a lot of techniques you can find out. So there are sometimes lossy compressions are there, non-lossy compressions are there. This is a huge area in case of image processing, image compression, compaction, in communication and lot of things. So, a lot of theory exists in case of compression and again recovery and all those things. So, that is not within the scope of this course. So, what we will see? We will see two very simple what you call compression techniques, what is the number of ones and the transition count at the output. So, there are other you can see there are lot more kind of compression techniques like LFSR based compaction, multiple input signature register based compaction and so forth. So, that I mean they are all part of the advanced testing kind of a stuff. So, as I already discussed in the course that this course covers overview of testing, design and verification in a one umbrella. So, we are not going in details of all this, but they are the two very basic compression techniques and we will be dealing in details with this. Okay. So, we will first see about the number of ones compression. So, number of one compression. So, what is the idea? So, the idea is very simple, it counts the number of ones in the output. Like for example, let us start with an area. So, this is, as on the name, it is a technique where we count the number of ones in the outputs of the circuit. So, it is let us see how it is a compression. So, what the idea is that if you look at the old, first LFSR we are studying in the circuit. So, this if you can consider about the first LFSR, that is the standard LFSR. So, this is the sequence of patterns to be generated. So, if you look at this will be our set of patterns which we required for testing. So, you have used this kind of LFSR. So, you just that is your assumption. So, that assumption is generating those patterns. So, you can see that these are your patterns. So, that is generated by that standard LFSR. Okay, so, now we are giving this as inputs. Let us assume that all these were very important for testing in our case. Now, if you assume the circuit is under normal compression, so it is a 1 0 0. So, the output over is 0, the output is 0. So, only in this case where all the inputs are 1 like this 1 sorry 2 3 4th bit. So, 1 2 3 4 4 this is 1 1 and 1. So, only in one case all the inputs are 1. So, the answer is a 1, all other cases the answer is a 0. So, if you apply the patterns from the standard LFSR discussed in the last class as inputs to this circuit, your output will be this one, all zeros and a 1 and then again 3 zeros. So, number of ones in this case is 1. So, what your ROM will record? The ROM will say that if you are using the standard LFSR, if you are giving us this as an input from that one, that is 3-bit LFSR, if it is LFSR, standard LFSR, in the last example we are giving as an input, the ROM will say that circuit under normal case will have only a single one. So, the ROM will now store only one for this whole set of inputs. But if you are storing what you can call, if you are using this flat storage, then what will be the case? You have to store this whole 1 0 0 1 and so forth. But now if you assume that there will be a lot of outputs from the circuit, then you can assume that the number of responses that have to be stored in the ROM has to be for this output, for this output, for this output, for this output and for this output, which would be quite large in number increasing the size of your ROM. So, even if in case of a single bit output, your ROM should have stored this whole value for this series of inputs. So, again this will take a large size in the ROM. So, we have done a compression. So, what is the compression like? So, it is the number of ones in the circuit. So, in the output of the cut. So, there is only one. So, you store a 1. So, only 1 bit is wasted in your ROM or 1 bit is required in your ROM. Now, let us consider a stack at 1 fault over here. So, a stack at 1 fault will make all these case all ones, like if this is one vector, this one vector, this one vector and so forth. Some 7 or 8 vectors were applied, 7 vectors were applied because all zeros cannot be applied. So, this is our standard LFSR which we are using. This was the characteristic polynomial, already we have seen that. Okay, so, now you are this is stack at 1. So, for all cases, so if you apply here 1 0 0, so in the normal case the answer should be a 0 is applied. So, in the normal case it should have been a 0 over here as you can see over here. Okay, but now it is the stack at 1 fault. So, every time it will be a 1. So, we will have 7 1s because in the series of the 7 test patterns 1 2 3 4 5 6 7 test patterns are applied. So, in this case every instance will be a 1 because of stack at 1 fault. Now, this again it is normal. So, you get this value same over here, but now in the previous case, so I mean we got only a 1 over here, but in this case we also get a 1 over here because in this case we will get a 1 over, because of this case we have another instance of all ones. So, we get the number of ones as 2 in this case. So, if you just apply all the patterns with the stack at 1 fault over here, so you will find out that there is one more instance of this one where both are 1 and you get the answer as a 1. So, here the number of ones is a 2. So, now what happens if you apply this set of patterns and this set of patterns and the ROM used to have stored 1, but output response here is showing 2 ones. So, in this case you detect that there is a stack at 1 fault over here. So, in this case we can say that what is the requirement? The requirement is a ROM with a single bit ROM over there and a single bit 3-bit LFSR with this one. So, it can test a stack at 1 fault here. Similarly, this set of patterns can test a series of other faults over here, okay, that we can easily find out, but by using a 1 bit this thing. So, the emphasis here is that, so we have done a compression from 7 bit to a 1 bit, that is by counting the number of ones, and there was no aliasing for this fault. So, no aliasing for this fault means what? That is even with this compression, if the fault is there, it can be detected, and if the fault is not there, that also can be detected. Now, to explain more explicitly, we will take an example where there will be aliasing. So, now just let us just repeat what I was saying about one's compaction. So, in the last case we see that 7 non-similar patterns, I mean there is no repetition patterns were applied to the LFSR, and the circuit generated this one. So, the number of ones is a 1. So, this is a compression. The same circuit when the stuck at fault, there are 2 ones. So, number of ones is a 2. So, as there is a difference in the number of ones, so the fault is detected. So, we can say that number of ones based compaction is non-aliasing, because in this case the fault could be detected, is non-aliasing for the fault. So, it may be noted that the corresponding to input values of 1 is stored as a golden signature in the memory, which is compared with the response of the card. So, that is a single bit response compaction, but the more important stuff here was that that is the fault could be detected, and so there was a no compaction in this one. So, again, but now we will see that it is not life is always as green, as I always tell. So, now in this case we will see another example where there will be aliasing. So, this let us take another circuit in this case, and the same sequence of inputs are given as this one, because I mean you are using this circuit because it is generating a near exhaustive set of patterns accepting the all zeros. So, you apply this, so you can easily find out what will be the values over here. And here if you find out this value, so it will be, so like it, I mean there will be there will be 2 ones in this case, because if you find out this is OR gate, so this is one instance and this is one other instance. So, in the 2 instances there will be output will be 1. So, number of ones in this case is equal to 2. Now, let us take a case where there is a stuck at 1 fault over here. So, stuck at 1 fault here means all these cases, every time it will be a all ones will be the case. So, if you consider stuck at 1 over here, so in this case we will have in case it will be always a 1 over here, and in this case it will be always a 0 over here. So, in this case if you do, so yeah, so now if you can do it over here, so just if you can try it out over here. So, let us make these things more simple. So, what we can do here is that, so it is a, so the pattern here is, so you can just say, I am just sorry over here. So, you can just say that is the pattern is all ones, because this one is connected to here, it is a stuck at 1 fault over here. So, and again you can see that this one is all ones, so it is all zeros over here, and if you can just compare out the values, so you will find out that there is this here. You can just compare out the values and just compute it. You can easily find out this will be a 1. So, because this is stuck at 1, so every bit will be a 1. You can easily find out. So, there will be 2 instances of 1s here. You will be able to find out. So, again in this case, what happens? There will be a number of 1s will be equal to 2, and that is actually a aliasing. So, what do you mean by aliasing over here? That is, if there is stuck at 1 fault over here, then what happens? That is, the number of 1s will be 2. The number of 1 positions are different. That you have to very easily have to identify that. Number of ones in this case is also 2. Now, if you stuck at 1 fault over there and you apply the same pattern, that is obvious, and then the number of ones are also 2. So, if you are using a number of ones counting as the compression, so it will say that for these patterns the circuit is having no fault, but that is an error because there is really a fault over here. So, that is what is called an aliasing, that is by compression that of ones, by counting the number of 1 compaction if you use, so you are going to get an error. But you can see if I have stored the flat representation of this one. So, what do you mean by a flat representation? Flat representation means whole this one is stored and whole this one is stored. So, you could have immediately caught that there is a fault because there is a mismatch at this point, and there is also a mismatch 3, 4, 5, 1, 2, 3, 4, 5, 6 position there is a mismatch. 6 position this is a 1 and this is a 0. So, you can see there is a mismatch in the first position and there is a mismatch in the 6th position. First position there is a mismatch, 6th position there is a mismatch. There is 0 and this is a 1 over here. So, you could have easily caught this fault. But now, because of this compaction, what has happened? It has gone about that you could not detect this fault because of the compaction, both the case the number of ones is a 2. So, that is actually called a aliasing based compaction, because it is a lossy compression, because from the number of inputs, number of ones equal to 2 and the number of ones equal to 2 here, you cannot regenerate this vector, and if you cannot regenerate this vector, you cannot find out there is a fault. So, it is a lossy compression, and because of the lossy compression, for this fault there was an aliasing. So, that is what I already told you, that now your RAM needs to store only 1 bit information kind of, means one integer, just one integer information. So, in this case 10 you can store in the ROM, that corresponds to the value of 2, and you need not store this long flat value kind of a thing. Okay. So, I mean that is the idea. So, the long value is not required to be stored. So, you save a lot of memory in the RAM. So, the RAM size is less, but what you have to pay that for some of the fault cases there can be aliasing as in the last case. Okay. So, that is what is being told over here. So, this is the output when the number of 1s is 2 and the circuit is normal. So, now this is being generated when the circuit is fault. So, you can see that there is a difference in these 2 points, but both the cases the number of 1s is 2. So, this kind of a compaction cannot determine that stuck at fault. So, that is actually called a aliasing, that is for the stuck at 1 fault that LFSR is aliasing has happened. Okay. So, now if you say that aliasing has happened, so you have to just determine that your fault coverage, I mean what you can call your fault coverage has decreased. So, you have to find out a reasonable fault coverage, because in BIST we generally cannot try out a very high amount of fault coverage, because we target only the many most important faults or the faults which are more prone to be developed. So, like say some parts of the circuit where there is a lot of congestion in the layout, or where there is a lot of hot spots, or where the circuits become more hot kind of a thing. So, you can enumerate which are the more dangerous area, or where are the areas where faults more tend to be or where faults are more tend to be developed, or faults are more prone to be developed, that you can find out from history, or you can find out from the layout graph, and all those stuff are there. So, you can find out which are the more important patterns that requires to be tested, or more important fault site to be tested. Based on that, you can find out which compaction scheme you have to use, because if you are using a compaction scheme, it will reduce the area of your ROM, but at the same time you should understand the fact that there will be aliasing and fault coverage will decrease. Now, which type of we will see another technique here. So, you will understand that, I mean for one technique some faults will be having aliasing effect, and the other for others there will be another set of faults which will having an aliasing effect. Like in case of this counting one, so this fault was aliasing, had an aliasing effect, and the other fault was not having an aliasing effect, and we will take another example where the case will be reversed. So, you can select the aliasing the compaction technique accordingly, and find out that what is the required coverage and which are the most important faults you want to target. So, in that way you can what you can say that you can get a smaller ROM size, as well as you can able to get a good coverage for the important faults, or the faults which are more tend to have been or developed when the circuit is in operation, right. So, there is another important compaction technique which is called the transition count. So, that means say again same circuit we consider. So, these are the inputs say, and these are the output you say. So, what is the transition count? Transition count, as the name says, you have to count when you go from 0 to 1, and another you have to say that when it is going from 1 to 0, that is in this case you say 0 to 0 no change, 0 to 0 no change, 0 to 1 there is one change, and then again 1 to 0 there is another change. So, transition count is 2. So, what is the transition count? Transition count means there is a change from 0 to 1 or a 1 to 0. So, in this case there are 2 changes. So, the transition count is a 2 over here, right. Now, if you take a stack at 1 fault over here, as already was discussed in the case. So, this is your all ones over here, and then we already know that this was your output in that case. So, what is the transition count over here? So, till here no problem, this is one transition. Here there is no problem, one transition. So, again the transition count is a 2. So, as I already told you, so if you select your compaction scheme as transition count, then this fault which was having a non-aliasing effect when you were using the other technique, that is now counting the number of ones. So, here the number of ones is 1 and the number of ones is 2. So, if you are using the number of one count, that is number of ones, if you count that technique, if you apply. So, if you are using the number of one counts, as I was discussing, so if you are using the number of one counts over here, so in this case you are good, you are lucky, because that fault is not having aliasing effect. But now, if you are selecting your scheme as the number of transitions, then what you are going to have? The number of one transitions if you are using, so the number of transitions you are using. So, in both the cases with and without the faults, you are going to have a same as the transition count, and there will be an aliasing. Now, just the second circuit you considered. So, this was the circuit, this was the stack at 1 fault. So, you can this one. Okay. So, this is video 1, sorry, because of this is the stack at 1 fault. So, this inversion also same circuit we have to consider. Now, this one is your output here, and with the fault this one is the output. Now, if you consider here is that number of transition is up to this, there is no transition, one transition same, and the transition count is 2. But now, if you look at this output with the fault, so the number of transition count is one transition count same, then one transition count, another transition count. So, transition count is 3. So, in this case the fault is detected. But if you look at the number of ones, it is 2 over here, and in this case it is 2 over here. So, for this circuit and this fault, counting ones is having an aliasing effect, whereas the number of transitions or the transition count response compaction is not having an aliasing effect. So, that is what I told you is that depending on circuit, depending on faults, and depending on the compaction technique, there can be different aliasing effect. So, therefore, what you have to do, you know what are the patterns that will be generated, you can decide that by your random pattern generated by that your LFSR design. Now you have to find out a compaction scheme. Then you have to find out that which are the most important faults and which are getting detected and which are not getting detected because of the aliasing effect. Then accordingly you find out your coverage and you do your design. Basically it is a multi-criteria optimization problem, as you can see. So all are interdependent variables, like say there are 10 very important faults which you need to detect, and this is a ROM area, you know, so you have to find out which is the best compaction technique. So depending on the best compaction technique or depending on the compaction technique, some faults will be detected and some faults will not be detected. Again, which faults will be detected will depend upon which input patterns you apply. So if you have an exhaustive test pattern generation, like if you are using a characteristic primitive polynomial, then it is fine, but sometimes we may not be using a primitive polynomial because we may want a much smaller area of the LFSR, or you may not be wanting the full path generation because that may lead to much more area. Then what is the case, you can use another LFSR without the primitive polynomial. So you do not go for exhaustive pattern generation, but you can have whatever is required, that number of patterns. But again, for a compaction technique you have used and the subset of test patterns you are using for this pattern generation may have a very high aliasing effect. That means what? That is, you have taken a compaction scheme. Now that compaction scheme is determining which are the test patterns you have to apply. So for example, you are selecting a compaction pattern, compaction technique which is very good, area is less, and you are getting a very less aliasing effect, but the test patterns to be used are say this one, this one, this one, this one and this one, all alternate. So if you are using all alternate, then you are in a problem, then you have to run through the whole LFSR and it will take time. But if you are using a compaction technique, same compaction technique maybe you are using, and if you are using this sequence of test vectors, then there is a lot of aliasing effect. So then you are at a problem, then you have to use this one, the alternative test, and it takes a long time to generate. And also another case may be there, in which case it may be case that if you are using only these 4, then only these 4 vectors if you are using, and you can use you are using a compaction techniques, then your coverage is very high. Then you are at a great design, then your life is good, because only by using these 4 consecutive patterns you can apply very quickly from your LFSR, and all the faults are tested by the compaction technique. So that is why it becomes a very important design challenge, that given a compaction technique, or sometimes you may have to require to change the compaction technique, because for example if you know that if I apply these alternative patterns, it takes a long time to generate. So what I can say that, can I have these patterns, or can I have at least up to this number of patterns, some one of them, so that I can generate these patterns very quickly from this LFSR, but still the compaction technique will give me a less amount of aliasing. So all those needs to be studied by looking into test vectors, and there are a lot of CAD tools over here which will tell you the results, that you are given a circuit, then you are saying that if I want to set these are the test patterns and these are the compaction technique, what is the fault coverage. Then it may, if you are getting a very low coverage, then you have to either change your compaction technique or change the patterns from here, and so forth. So again, that is why I told you it is a iterative solution. So by looking at all these things, you have to decide which test patterns you have to apply, which is the compaction technique you will use, and depending on which test pattern you will apply, you can decide on your characteristic polynomial, you can decide on your seed. So that is why design of a BIST is a challenging problem, so that you can appropriately cover most of the faults, and at the same time you can do that very quickly using the initial set of patterns determined from the seed from a standard or a modular LFSR. So that is a very important step. So I mean, one most important thing before we stop for this discussion, that is, so what like the two whatever you say the 2 compaction technique is told. So what is the gain? So if say it is an n bit output, so if it is an n bit output, then what is the gain in the storage? So if the now what is going to be the, so it is n bits output can be there. So if there are all ones, then what will be the case? Then you require how many bits to store it? So there will be n number of ones. So what is the number of bits required to store n? It will be log 2n. Similarly, transition count can be what? So 1 0 1 0 1 0 1 0. So 1 2 3 4 5 6. So it can be again on the order of n. So if you are storing this in flat, so you require n bits to store. You storing this in flat, you will require n bits to store. But if I count the number of ones, so if everything is 1, then in the worst case the value will be n. And how many bits are required to store n in a RAM? It will be log 2n. Similarly, in the case of transitions, so transition count, so in the worst case there can be always there can be flips, and the value can be at most in the order of n. So number of bits required to store n in a RAM or in binary is again log of 2n. So if the RAM size, if you store this outputs flatly, so you require n bits to store it, okay, if the output is n bit length. But if you are using the 1 count or transition count, so you require log 2n. So that is the amount of factor we have saved in this case of this one. In this case of this 2 compression scheme we have seen. But again, sometimes there is an aliasing effect and all those things. Now, also have to understand the fact that for one such output n to log n you have saved, but if there are large number of inputs, so you will be saving in for every output you will be saving the value from n to log of n. Okay, so that was about our discussion on what you call BIST architectures. So, we have discussed the two very important components of BIST. One is the random pattern generator, which is using an LFSR, and then also you have seen this other most important component of BIST, that is your response compaction and comparator. So, the comparator here is very simple, it is comparison with 2, comparison with 1. So, it is just a bitwise comparison you can use, but the very important part is that how you can compact your output response. So, compaction should be such that your aliasing is minimized. So, in this case we have given examples that given the circuit, given the fault and given the input pattern, and the compaction nature, the aliasing values will change. So, it is a design problem and you have to find out which one is the best for you. Okay. So, now we will go to the question answer session. So, in a BIST, how do you know which LFSR is to be used for test pattern generation? That is a very important problem that we are just discussing now, that given a circuit, how do you design, how do you decide which is the LFSR, how do you decide which is your pattern generator, I mean how do you decide which is your compaction technique, how do you decide what is your seed. So, all will depend on how quickly you can do your testing and with the minimum, that is with the minimum number of vectors and how good coverage you can get. These are the two main things you need to achieve. Okay. So, first is that the width of the LFSR as is the number of inputs of the circuit, that is very obvious. If you have an n input circuit, then there will be n bits required in the LFSR. So, it has to be n bit circuit, that is obvious. So, that is generally. Secondly, the characteristic polynomial should be primitive polynomial, that it generates all possible patterns. So, the general statement, if you are general case, in most of the cases you would maybe require all patterns to do the testing. So, you can go for a primitive polynomial, but also there are other cases in all zeros cannot be generated, as we will see very soon. So, other way you can find out that you can find out which is the most important patterns required to be generated. So, accordingly you can set the primitive polynomial, you can use the, it may not be the characteristic polynomial may not be primitive if you are targeting only a few of the vectors that you can do. And also, so but for exhaustive pattern you can use the primitive polynomial. So, if you are using a primitive polynomial, all patterns will be generated, but if you can solve your testing stuff with a good coverage and non-aliasing thing with a few initial patterns kind of a stuff, then you also can go for a non-primitive polynomial. Thirdly, the seed. The seed is very, very important, as I told you. So, you have to generate the seed in such a fashion so that the initial patterns can do your testing for the coverage. So, you select this one. Following that, the compaction technique, as I have used. So, you have to go for find out a good compaction technique. So, what is a good compaction technique? That which is going to give a minimum amount of aliasing for the set of patterns which you have decided using this LFSR and the seed. Now, again, as I already told you, these are not sequential problems to be decided. Sometimes you have to go back and iteration. So, sometimes you can find out that whatever aliasing problem you have taken or aliasing scheme you have taken, there is whatever compaction or compression technique you have used, there is a lot of aliasing because of the patterns you have taken for this. So, you have to again go back and require a different set of patterns. Sometimes you can find out that for using the different set of patterns which are giving you a low aliasing, the area overhead of the LFSR is becoming very high. So, what you can do, you can change the compaction technique. So, these are the three or four steps which you require to design an LFSR, or what you can say that design a BIST architecture or BIST circuit, but again these are all interdependent problems and you may have to go for iteration, right. So, that is the answer to the first question. In the case why an LFSR cannot have all 0, the answer is if the seed is all zeros, the LFSR will be stuck at all 0 stage as the feedbacks for all zeros are LFSR, as the feedback logic is XOR gates. So, like for example, if you have an LFSR as we already seen, so in this case, so just modular LFSR, if you consider something like this. Now, the seed is 0 and this one is also 0, this is a feedback from this one thing. So, 0 XOR 0 is 0. So, everything will be stuck off. So, as all the feedbacks in the XOR gates are, so all the feedbacks in the LFSR or modular LFSRs are based on XOR gates. So, if everything is 0, the XOR of a 0 and a 0 is a 0, so whole thing will be stuck to 0, you cannot do that. So, if you are very adamant or if it is very much required to have a 0 as a pattern, so that has to be applied explicitly. That has to be applied explicitly, you cannot do that. You should have a separate smaller subcircuit which will apply all zeros and do the testing, because the LFSR will generate all the other patterns. So, with this we come to end of our discussion on BIST. So, in the next class or in the next part of the course, we will have another very interesting part, that is actually the memory. So, till now we have seen circuits, how to do the circuit in the offline mode, also we have seen the circuit how we can do the testing in the in situ mode, that is in the BIST. So, there is a third part of your circuit which I have not yet talked, that is the memory. Memory is not an ordinary combination or sequential circuit, it is a specially designed circuit which stores a lot of values or lot of binary values in your circuit without taking that much amount of area. So, simple test schemes that you have seen like your D algorithm, ATPG, sensitize, propagate, justify do not generally hold for a memory, because memory architecture is quite different from normal sequential and combination circuits. So, in the next few lectures we will be discussing about how you can do testing of memories. Thank you.